Hi, I'm Henrik Mårtensson. About a week ago, I was in Linköping at the DevLin 2025 conference. I had been invited to speak and I held two presentations there. And this is one of them. This is my presentation about reference class forecasting, a method of making effective prognoses of duration and cost in projects.
So, welcome to this little talk about statistical forecasting. We're going to begin this talk by going straight for the jugular. We'll talk about time estimates. And don't worry about the slide, it's just strawberry jam. Every software development organization I have worked with the past 40 years has had the same problem with time estimates. They are almost always wrong. It doesn't matter which method you use to make the estimates, poker planning, t-shirt estimates, critical path, critical chain, they rarely work. And yet, very few organizations take a serious look at the problem. Instead, they just live with it, or they keep switching between different estimation methods without ever getting reliable results. Now, in particular, they don't consider whether estimation is the right thing to do, and they do not consider whether there are alternatives. There is actually a name for this. It's called single loop learning, and this model was created by the organizational behavior expert Chris Argyris. In single loop learning, we have a mental model of how something works, and based on that model, we have a set of decision-making rules. In this case, we have a mental model that says project duration and cost can be predicted by decomposing the project into parts, estimating the parts, and adding the estimates together. Thus, what we need to do is to select the best way of making the estimates. Now, in many cases, single loop learning works well enough, but if there is something wrong with your mental model, you will never find a good solution. Now, Chris Argyris came up with another learning model, double loop learning. In the double loop model, the feedback we get changes our mental model. When our mental model changes, our decision-making rules change, and we are suddenly able to look for new solutions to our problem. Today, we will go from single loop learning to double loop learning to solve the problem of bad estimates. So first, we will ask ourselves why we need estimates in the first place. And this may seem like a dumb question. It's pretty obvious we need them to predict when something will be done and what it will cost to get it done. So we'll dig a little bit deeper though. We use estimates to decide if something is worth doing at all, and that is, we make go, no-go decisions. And we use estimates to decide how and when to allocate people and resources. And we use estimates to synchronize activities, and we also use estimates to time box activities, for example, during sprint planning in Scrum. Now, as it turns out, that last one is not really necessary. Projects work better without time-boxed sprints, and we'll have a look at why in this presentation. The American journalist H.L. Mencken once wrote that for every complex problem, there is a solution that is clear, simple, and wrong. And Mencken himself had some questionable views, so he was in a good position to know. Now, he had a good point though. Sometimes the clear, simple solution is the wrong solution. It would be nice if we could find some way to test if estimates are the right solution or if estimates are one of those wrong solutions. Now, all estimation methods, from the simplest to the most complicated, are based on the idea that we can make a guess about how long a unit of work will take or what it will cost, and that the guess will be so close to the actual result that it's useful for making decisions. Ideally, if we plot estimates against actual outcomes, in this case cycle time, in a scatter plot, we will get a straight line. Now, if we look at real data from a project team, what we will see is almost always very different from what we expect. We don't get a line. Instead, we get a cloud of more or less random points. If we build a frequency distribution table of actual job durations, we will get something like this. Quite a few jobs are done very quickly, but some of them take a lot longer, and there is a long drawn out tail that can stretch out a long, long way. It does not really matter if we look at cycle time or lead time or which team we look at. Almost all teams have this kind of long tail distribution of job durations and randomness when you plot estimates against actual outcomes. It's the same with every team I've looked at over the past 6 or 7 years. The estimates don't work. The distributions of job durations tell us a bit of why. They don't follow anything close to a normal distribution. Instead, they have long tail distributions. Also, note that the distributions are quite different for different teams. It's pretty clear estimates don't work. We need to do something different. I'm not the only one pointing out this problem with estimates. In a 2025 research paper, Uniqueness of IT Cost Risk, the researcher Bent Flybjerg and some of his colleagues show that IT projects are more unpredictable than any other kind of projects. Flybjerg's research was inspired by ideas by the Nobel Prize laureate Daniel Kahneman. Now, Kahneman noticed that he and his colleagues never got it quite right when they estimated their projects. He figured out that the reason was that there are simply too many unknown factors in a complex project. Not only that, the longer a project lasts, the greater the risk that there is some unforeseen delay that wrecks the estimates. Kahneman also figured out a solution. Flybjerg and his research team developed it further and used it in real, very complex projects. And it's that solution that we will explore. First, let's specify what we mean when we ask for a time estimate. For a customer, a manager outside the team, or a product owner, the most interesting thing to know is the lead time. That is, how long it takes to implement an idea from when we first give a requirement to a development team until users get finished functionality. And let's break the timeline from start to finish down a bit. If we have a Scrum team, the first thing that happens is the requirement is written down, often as a user story, and put in a product backlog. There it lies waiting until the team has time to do something with it. Eventually, the team has a look at the requirement, refines it a bit, and sticks it into the sprint backlog. The requirement lies waiting a relatively short time in the sprint backlog, then the team works on it. We often measure the cycle time as the duration from when the team begins to work on a requirement until the team is done. Now, it's worth noting that we can measure cycle time from any point in the process to any other point, so it's a good thing to specify which cycle time we are talking about. After the team is done, there is a wait until the software functionality is deployed. Now, if the team has continuous deployment and it works, this time may be down to a few minutes, but it may be considerably longer. Summing it up, in most cases, this is what the business side wants to know. The unit of work that business is interested in may be the lead time of user stories, features, capabilities, epics, use cases, an entire story map, a sub-project or a project. Programs, of course, do not have a defined end state, so the duration of a program cannot be predicted. Instead, a program is run until it's no longer profitable. Scrum teams focus on the cycle time from when they begin to work until they are done, most of the time. So we will have a look at this first. I'm pretty sure many of you will think, but we estimate effort, not time. Well, the team does capacity planning for a time-boxed sprint, and no matter what you call it, what you do is trying to figure out how much work you can fit into the time box. As we have already seen, this is like trying to predict the outcome of a die roll. To make it worse, the die is uneven, so it has a wonky probability distribution. So why is this such a problem? Let's make a thought experiment. We have got a user story and we want to make an estimate. So what's the best estimate? There is no single place that looks like the best guess. The reality is the actual duration can end up anywhere within the probability distribution. There is no single number that represents a good guess. This has consequences when we use estimates for time boxing, as in Scrum's sprint planning. If we look into why we do time boxing, there are a couple of common reasons. We fight procrastination, we focus on work that matters, we want to achieve something complete and meaningful. And the problem is that if the estimates don't work, then the time boxing will not work. So let's have a closer look at what happens. Here are 5 user stories. Let's estimate. Each user story has a duration within the probability distribution. So we make the best estimates we can, but they will end up a little bit different. Based on the estimates, we determine we should be able to do these 5 user stories in a sprint. If we sum up our estimates and show the sum on a timeline, it looks like this. However, any one of the user stories has a fairly high probability of taking a lot longer than what we estimated. There is also a probability that a user story is finished faster than expected, but the probability distribution is asymmetrical. Gains tend to be small while losses can be very large. So if we look at the probability distribution for all of the user stories together, it's a lot longer than a single sprint. This means we tend to overestimate how much work we will finish in the sprint. When that happens, it becomes impossible to finish within the time box. We fail to meet the expectations over and over again. And this can turn the time boxes into torture chambers and demoralize the best of teams. Don't freak out, it's still strawberry jam. So therefore, time boxing is not such a good idea. Add to this that in Agile, we already have practices and techniques that accomplish all of the things time boxes are supposed to do, but in a much safer manner. Fighting procrastination, well, we do that with pull processes, pair programming, troikas, and other practices. Focus on work that matters. Well, prioritization, pair programming, and troikas help there too. Achieve something complete and meaningful. Well, we do that because we work with vertically sliced requirements like user stories, features, use cases, and we thin slice them so we get thin slices of complete and meaningful things. We also work with cross-functional teams so the team can work on something and finish it. They don't need to hand it over to other teams. And well, unless we have really large projects. And we have T-shaped training where we train developers and their managers to a very high degree of competence. In early Agile, we talked about training like a marine, and this is something that you can find in early books about Agile methodologies and toolkits. So a fairly easy way to eliminate time boxing is to go fully pull process. Get rid of the sprint backlog, put a hard working process limit on the product backlog, make a rough prioritization, pull the top item off the backlog, refine and implement. When done, pull the next item off the product backlog. And it could look something like this. In case the idea of changing Scrum makes you nervous, I want to remind you that Scrum is a framework. A framework is a supporting structure. You can build a working methodology based on Scrum, but Scrum is not intended to be a methodology all by itself. A methodology is a system of values and practices that support and reinforce each other. In Agile, extreme programming is a good example. Methodologies need to be adapted depending on the context they are used in. Generally speaking, adapting a methodology is easier than building a methodology based on a framework. Finally, a toolkit is a collection of methods you can use to flesh out a framework to create a methodology, or you can use it to adapt an existing methodology so it fits your context. So you shouldn't be afraid of changing the Scrum framework. You should be afraid of not changing the Scrum framework. And one important thing is that Scrum is supposed to be immutable, but the practices and artifacts in Scrum are context dependent. So if your context doesn't fit with Scrum, you can either change the context, which is usually really difficult to do. You can stick with Scrum and have something that works only so-so, or you can abandon the idea that Scrum is immutable, and technically you also abandon Scrum then, and do the adaptations that you need in order to get things to really work. But that is for another presentation. So let's move on. So where did we go wrong when trying to figure out when a user story is done? We need to go back to the drawing board and look at the problem using another perspective. What if we look at the statistical probability distribution and treat it as, and this may be a shock, a statistical probability distribution? At some point along the x-axis, the duration axis, 50% of all user stories will be done. I think we can agree on that. That means at another point, 70% of all user stories will be done. And this is getting a bit repetitive, but there is also a point along the x-axis where 85% of the user stories will be done. And for the team I'm showing data for here, this is 22 days. This means if you pick any user story at random, we can say it will be done in 22 days with 85% probability of being correct. In theory, we could decide what probability we want of being correct and then use the probability distribution to figure out the duration. You may ask, how difficult is it to do that? Well, I'm glad you asked. It turns out we can do that easily with the percentile function in Excel, and I'll show you how. Okay, what we have here is an Excel spreadsheet where I have exported data from Jira, data about a project. And I can look at cycle times, and I have sorted them in this case, and I use the percentile function in Excel in order to figure out what the 50th percentile, the 70th percentile, and the 85th percentile is. Now, one important thing, what you see up here is aggregate, and aggregate it's kind of a multifunction thing that can do percentiles. And I use aggregate, it's my habit, because if I start filtering data, aggregate will work, but the percentile function will ignore the filters. So that's why I'm usually stick with aggregate. And here we can see the 85th percentile, and we probably want to be 85% certain in our prognosis. That's 22 days. Now, while we're looking here, so this is really incredibly simple. We just enter the data, we use the percentile function, and we get our prognosis. Now, one thing we can do that is really cool is that if we look at open issues that a team is working on, then we can do something, then we can use the same kind of system to actually reduce cycle time. Here, we have data from a team, and we're now looking at several different kinds of data. So the first thing we'll do is that we'll filter, and let's say we want to filter on features like this. Now we can see that we've got an 85th percentile of 206 days. This is a team that was in trouble. And we can see from the graph I've constructed here that we have a few items that are way above the others. The green line is the 50% line, the yellow line is the 70% percentile line, and the red is 85th percentile. Now this means that if we prioritize according to age of items that we are working on, then by finishing these, we can actually reduce the average cycle time by a lot. So it can be very, very useful for us to prioritize based on the age of items, and we can use the percentile function for that too. That's just a little bit of a bonus. And that is pretty much it. Reference class forecasting is completely data-driven, so no one has to do any guesswork whatsoever. If you have reliable data, the method is easy to implement. You need to have a stable system for reference class forecasting to work, and to do that, you can use established agile methods for controlling flow and code complexity. Remember that Scrum is not a methodology. You will need to look at methodologies and toolkits to learn what you need to do and how to do it. This, however, is nothing new. I will advise you to go directly to the sources to learn more. I first learned about reference class forecasting from Daniel Kahneman and began figuring out how to use it in practice. Then, when I found Bent Flyvbjerg's white papers and his book, How Big Things Get Done, I had what I needed to verify that I had understood Kahneman's ideas correctly. And don't forget that if you switch to reference class forecasting, you need to check that it works for you. Don't repeat the mistakes almost everyone does with estimates. Finally, the struggle for improving how we work goes on. Never give up, and thank you for listening.
Okay, so that was reference class forecasting. I had only 25 minutes for the presentation, and the Swedish version at the conference, well, I didn't quite make it through because of a slight delay. But even so, I had to cut out a lot of material that I think would have been interesting, and one of those pieces of material was Monte Carlo simulation. Monte Carlo simulation is an older method for making statistical prognoses, and it's still valid today. It's a bit more resource intensive. You need software that can run the simulation, but it's a perfectly valid method to use, and we have had it in project management since 1963, so it's pretty well tried out. I encountered it for the first time in the 1990s when I hung out in Yahoo groups with project managers who refurbished nuclear submarines, and they used it because their projects were so complex that it was impossible to come up with good time estimates. Now the question, reference class forecasting and Monte Carlo are a little bit different. You can ask different questions. So for Monte Carlo, you can ask questions like, how many of this kind of item will I be able to do in a certain time period? Or you can ask questions like, if I have this time period, how many items will I be able to finish? So it's a bit different from what you do in reference class forecasting. But both methods are very useful. I chose to talk about reference class forecasting because reference class forecasting is fairly easy to implement. If you want to get the most out of this video, if you like it, then show it to your friends and teammates. And you may even want to show it to a manager if you think they are receptive to improving the way you work and maybe have more accurate prognoses. I think that's it. I'll be seeing you.